Good evening, ladies and gentlemen. How is everyone doing this evening? Why pain? Why tired? Exhausted? I'm doing well, thank you. Okay, so lots of work. A long week, but a week has only started. This week has been a long year. No, I understand. But you guys will get used to the workload and everything. So just hang in there for a few more months to get used to everything. So let's give it another minute or two and see if more of our class friends join us. I know there's some sort of a semester test happening tomorrow. Not sure for which module, so class participation might be a little bit lower this evening. But let's give it another minute or two and see how many more people will join us. But while we are waiting, just a bit of admin. So next week, Monday, the 21st, is a public holiday. So we will have no class next week, Monday, but we will have class next week, Tuesday. So next week, Tuesday, I will also be on campus for consultation again. So what semester test are you guys writing tomorrow? No, not this module. This test is only in May. So before we start with tonight's lecture on the sun, I want to show you two other videos as well that will prickle interest for the following chapter we're going to do. And this chapter is going to build on this chapter. Yes, this coming Monday, the 21st, is a public holiday. Because we only have a one semester test. And the other big thing you do for marks is your assignment. So that is in the study guide when the semester test is. Let me just quickly check. So the semester test is the 27th of May. So things due on Monday, that's interesting. Your lecturers should have taken that into account. Well, let's begin tonight's lecture with two short videos. So this video is a nice indication of how small we actually are and how big some of these objects are in the universe. So yes, a few of the questions. So first thing is, Venus is nicknamed Earth's sister. Yes, in some cultures, Venus is referred to as Earth's sister. Then why does only Saturn have a ring? So Jupiter also has a ring and Neptune also have rings. But it all depends on the gravitational forces destroying the rings and creating new rings, but we will discuss that in upcoming chapters as well. Then yes, all of these you can say as types of stars or suns. Yes, so we are atom size compared to the universe. You are correct. So how do they know the size of the universe? So we can look, and that is something we're going to discuss in later chapters as well. We know what the speed is the universe is expanding at, and we can detect the earliest traces of the Big Bang. And by doing the calculations, we can have an estimate of how big the universe currently is. So what is the Bootes Void? So Bootes is a constellation. And near Bootes, there's an area in space called Bootes Void, and we cannot see anything from the Bootes Void. So we expect it is a supermassive black hole. So now the next video I want to show you guys.
Little star. Oh, I know who you are.
One Gaia, please, for mankind.
At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light too. If you look through binoculars or take pictures of them, you'll see that they're all different colors too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force. Say it with me now. For science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object. But in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of two different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectra. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time it was thought that stars had roughly the same composition as the Earth. But Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today, and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic, "Oh be a fine guy, kiss me," or "Oh be a fine girl, kiss me," to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between, there are orange and even some yellow stars. But there are no green stars. Look as much as you want, and you won't find any. It's because of the way our eyes see color. A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together to form other colors. A star can actually emit more green light than any other color, but we'll wind up seeing it as white. How do I know? Because if you look at the sun's spectrum, it actually peaks in the green. Isn't that weird? The sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the sun is actually yellow. Not really. The light from the sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the sun, which is why the sky looks blue. The sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the sun a yellowish tint to our eyes. And looking at the sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the sun, so all the bluer light is scattered away. So we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise, a very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, but now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the Sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low mass stars like the Sun and higher mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today,
So this is a nice summary of what we are going to learn tonight and what we're going to learn in future chapters. But just to answer a few of your questions. So, sir, why would the sky turn a deep orange during a storm? So that is due to the principle of the Rayleigh scattering principle. And that's the same principle why during normal day our sky is blue, because that is green and blue and purple frequencies get scattered by molecules in the atmosphere. But during a storm, or before a storm, after a storm, there are, and especially also when there's dust in the air, that means your red and orange and yellow frequencies get scattered more, and that is why the sky then seems more orange. Then another question, when we see pictures of nebulas, they're very clear and colorful. Are we able to see them because of light they reflect, because of stars around them, or do they glow? So that is a interesting question, and it's a combination of both. So nebulas, the majority of nebulas are the birthplace of stars. So if we look at a nebula with different instrumentation through an optical telescope, infrared telescope, radio telescope, we can see that some of the stars in a nebula are illuminating the particles around them. That scatters and that causes pretty pictures. But some of that gas material also radiates its own energy, and we can see that as well. So it's a combination of both. Then another question. Sir, would you recommend we rewatch Crash Course videos we're preparing for tests and exams? So these videos are a nice way to get a quick recap of the work. So if you're struggling with a concept or just want a quick recap, then Crash Course videos will provide that with a nice recap for you. Pleasure. So for tonight's lecture, we are going to talk about the sun. But the sun has many aspects to it. So we're going to speak about the sun and what makes the sun tick. So the solar atmosphere, the photosphere, the chromosphere, the solar corona, the composition of the sun, what happens below the photosphere, observing the sun, solar activity, sunspots, the sun's magnetic cycle, chromospheric and coronal activity, the solar constant, nuclear fusion in the sun, nuclear binding energy, hydrogen fusion, energy transport in the sun, and then finally counting solar neutrinos. So, do you all recognize this and can tell me what this is? Yes, that is a solar flare. You guys are correct. And what else can you tell me about a sun? What interesting facts do you have about a sun? Yes, the sun is very hot. It has no surface. It has some sort of a surface that we were going to discuss now. It's made out of a hydrogen gas. So yes, you are correct. It's majority of hydrogen gas that's being fused. Yes, it won't become a black hole when it dies. Solar flares cause magnetic field lines get tangled and can't return to the first surface. Yes. The sun has an atmosphere that we're going to discuss now. The core generates electromagnetic waves. Yes, that is correct. It has a massive magnetic field. Yes, you guys are correct with all of those facts. So the center has plasma, sort of. We will discuss that in this chapter. So in the sun is the main source of light and warmth on Earth's surface. So it is a natural object of human curiosity, and we awe it. It is also the star that is most easily visible from Earth. We will discover how analysis of the solar spectrum can paint a detailed picture of the sun's atmosphere, and how basic physics solves the mystery of what goes on in the sun's core. So during this lecture, we're going to answer 4 important questions. So firstly is, what can we learn about the sun by observing its surface and atmosphere? Then secondly, what are sunspots? Thirdly, why does the sun go through 11 and 22 years cycle of activity? And then lastly, what is the source of the sun's energy? So can you guys tell me what this is in this image? So a few of you are correct. So this is a transition. So here we can see a sunspot. Here we can see a sunspot. But this is Mercury that passes through or in front of the sun. And that is called a transit. So I know there's some people, usually when there's a transit happening, they go to the best parts of the world to observe it. A scientist joked that solar astronomers would have a lot more about the sun if it were further away. The sun is so close that Earth's astronomers can see swirling currents of hot gas and arched bridges of magnetic force at a level of detail that seems overwhelming. The sun is made up of almost entirely of hydrogen and helium gas, confined by its own gravity in a sphere 109 times Earth's diameter. The gases of the sun's atmosphere are hot and radiate the light and the heat that make life possible on Earth. Do you guys guess from where this picture is taken? Yes, you guys are correct. This is Mars. This is taken from the sunset on Mars with the Curiosity rover. And this image, and this is probably one of the most famous pictures in astronomy. Yes, you guys are correct. So what happened here is, when you guys familiar with the 2 Voyager missions? So the 2 Voyager spacecraft or Voyager probes are the 2 man-made objects that are the furthest in space. So they are currently Voyager 1 is in the process of leaving our solar system. But when Voyager 1 flew past Saturn, the great astronomer Carl Sagan suggested that NASA swing the cameras around. And from this, we can see our sun. And then right here, that tiny dot is Earth. So this is one of the most famous photographs in astronomy. So the sun's atmosphere is made up of 3 layers. The visible surface is the photosphere, and above that are the chromosphere and the corona. Note that astronomers normally speak of the interior of the sun as being below or under the photosphere, and the sun's atmosphere as being above or over the photosphere. When you look at the sun, you see the photosphere as a hot glowing surface with a temperature of about 5,800 Kelvin. That temperature is determined by precisely measuring the spectrum of sunlight using Wien's law. At that temperature, every square millimeter of the sun's surface is radiating more energy than a 60-watt light bulb. With all that energy radiating into space, the sun's surface would cool rapidly if energy did not flow up from the interior to keep the surface hot. So simple logic tells you that energy in the form of heat is flowing outward from the sun's interior. Not until the 1930s did astronomers understand that the sun makes its energy by nuclear reactions at the center. The visible surface of the sun looks like a smooth layer of gas, marked only by a few dark sunspots that come and go over a few weeks. Although the photosphere seems to be a distinct surface, it is not solid. In fact, the sun is a gaseous from its outer atmosphere right down to its center. The photosphere is a thin layer of gas from which Earth receives most of the sunlight. It is less than 500 kilometers deep, and in a model of the sun the size of a bowling ball, this photosphere would be no thicker than a layer of tissue paper wrapped around a ball. The photosphere is a layer in the sun's atmosphere that is dense enough to emit plenty of light, but not dense that light can't escape. Below this photosphere, the gas is denser and hotter and therefore radiates plenty of light. But that light cannot escape because it's blocked by the outer layers of gas. Earth doesn't receive light from deeper layers under the photosphere. In contrast, the gas above the photosphere is less dense. So although Earth receives that light, there is not much of it. The photosphere appears to be substantial, but it's really a very low density gas. Even in its deepest, densest layers, this photosphere is less than 1 divided by 3,000 as dense as the air you breathe. To find gases as dense as the air at Earth's surface, you will have to descend about 15,000 kilometers below the photosphere. With fantastically efficient insulation, you can fly a spaceship right through the photosphere. Do you all recognize this image? What causes the nuclear reactions? We are going to discuss this in this chapter as well. But this image is to start the opening scene of Star Trek Voyager, where Voyager flies through a solar flare. So this is Star Trek. Aren't you guys Star Trek fans? So I'm a big Trekkie, so if you missed the series, if you ever have the time, please watch it. So do you think that the sun is in a perfect position to support life on Earth? Or did life on Earth evolve to make the sun's position perfect? So that's where we can discuss that in the last chapter. But Earth is actually at the correct position because Earth is in the Goldilocks zone. So I like to call it a Goldilocks zone because it's not too cold or not too warm, it's just right. So if you move closer to the sun, then it will be too warm. If we move further away from the sun, then it will be too hot. But as we will see during the life cycle of the sun, eventually in 4.5 billion years, due to the sun starting to die, the Goldilocks zone will shift and life will not be supported on Earth anymore. But that is something we are going to discuss in the last chapter. So another cool picture of the Starship Voyager. So if we compare it, so in image A, we can see a cross section at the edge of the sun, shows the relative thickness of the photosphere and chromosphere. Earth is shown for scale. On the scale, the disk of the sun would be more than 1.5 meter in diameter. Then the image on the right, we can see the corona. So the corona extends from the top of the chromosphere to the great height above the photosphere. The photograph on the right, made during a total solar eclipse, shows the inner part of the corona. So here we can see this, we can call it the photosphere and the chromosphere. So you guys happy with these definitions? Awesome. Then, from the previous chapter, we can also see the sun has an absorption spectrum that can tell us a great deal about the photosphere. So what elements are in the photosphere of the sun? We know from Kirchhoff's third law that an absorption spectrum is produced when a source of a continuous blackbody spectrum is viewed through a transparent gas. The deeper layers of the photosphere are dense enough to produce a continuous spectrum. Atoms in higher transparent layers of the photosphere and in the sun's atmosphere absorb photons with unique wavelengths and energies corresponding to the jumps between each type of atom-electron orbits, producing absorption lines that allow you to identify hydrogen, helium, and other elements. In good photographs, this photosphere has a mottled appearance because it's made of dark edge regions called granules. The oval pattern is granulation. Granules can be several thousand kilometers across, but last for only 10 to 20 minutes, each before fading, shrinking, and being replaced by a new granule. Detailed observations of the granules show that their centers emit more blackbody radiation and are slightly bluer than the edges. From this information, plus the Wien and the Stefman-Boltzmann laws, astronomers can calculate that the granule centers are a few hundred degrees hotter than the edges. Convection occurs when hot material rises and cool material sinks, as when, for example, a current of hot gas rises above a candle flame. You can watch convection in a liquid by adding a bit of cool non-dairy creamer to an unstirred cup of hot coffee. The cool creamer sinks, gets warmer, expands, rises, cools, contracts, sinks again, and so on, creating small regions on the surface of the coffee that mark the tops of convection currents. Viewed from above, these coffee regions look something like solar granules. The presence of granulation is clear evidence that energy is flowing upward through the photosphere. So spectroscopic studies of the solar surface has revealed another less obvious kind of granulation. Supergranules are regions a little over twice Earth's diameter that include about 300 granules each. These supergranules are regions of very slowly rising currents that last a day or two. They appear to be produced by larger gas currents that lie deeper under the photosphere than the ones that produce the granules. So now visualizing this. So in image A, we can see the ultra-high resolution image of the photosphere shows granulation. The largest granules here are about the size of Texas. So here in the image we can see this darker effect that it forms are granules. Then in image B, we can see how this is created. So here we can see we have rising hot gas, and that brings hot gas up, more energy. The gas starts to cool and it forms a granule, then it sinks back down. Then it gets heated up again, it rises again, and then it falls back down. Are you guys happy with this definition? Awesome. So another cool way that you can actually see granulation in granules. If you are making a pot of porridge, it can be wheat bix, it can be, not wheat bix, oats, it can be your normal pap, anything you want. If you put it on a stove and it starts boiling, it will make bubbles. And if you look below that bubbles, that is actually convection currents. So you will see more warmer parts, warmer currents rising, and then it cools down, and that will form granules as well. Above the photosphere lies the chromosphere. Solar astronomers define the lower edge of the chromosphere as lying just above the visible surface of the sun, with its upper regions blending gradually with the corona. You can think of the chromosphere as an irregular layer with a depth on average less than Earth's diameter. Because the chromosphere is roughly 1,000 times fainter than its photosphere, you can see it with your unaided eyes only during total solar eclipse, when a moon covers the brilliant photosphere. Then the chromosphere flashes into view as a thin pink layer just above the photosphere. The pink color is produced by the combined light of three bright emission lines, the red, blue, and violet Balmer lines of hydrogen. The chromosphere produces an emission spectrum, and Kirchhoff's second law tells you it therefore must be an excited low-density gas. Further analysis of a solar spectra reveals that atoms in a lower chromosphere are ionized, and atoms in the higher layers of the chromosphere are evenly more ionized. Astronomers can find the temperatures in different parts of the chromosphere from the amount of ionization. Just above the photosphere, the temperature falls to a minimum of about 4,500 Kelvin, and then rises rapidly to the extreme high temperatures of the corona. The upper chromosphere is hot enough to emit X-rays and can be studied by X-ray telescopes in space. A photogram is an image of the sun made using light only at a wavelength of one of those strong absorption lines to reveal detail in the upper regions of the chromosphere. Another way to study these layers of gas high in the sun's atmosphere is to record solar images in the far ultraviolet or X-ray portions of the electromagnetic spectrum. Because those layers are very hot and emit most of their light in short wavelengths. The following figure shows a photogram made at a wavelength of hydrogen alpha Balmer line. This image shows complex structure in a chromosphere. Spicules are flame-like jets of gas extending upward into the chromosphere and lasting 5 to 20 minutes. So here we can see in the image A is an hydrogen alpha photogram of the sun's disk. Then in image B, hydrogen alpha photograms reveal complex structures in a chromosphere that cannot be seen in ordinary visual wavelength images, including spicules springing from edges of the supergranules. Then in image C, seen at the edge of the solar disk, spicules look like a burning prairie, but they are not all relating to burning. The white circle shows the size of Earth to scale. The outermost part of the sun's atmosphere is called the corona, after the Greek word for crown. The corona is so dim that, like the chromosphere, it's not visible in Earth's daytime sky because of the glare of scattered light from the sun's brilliant photosphere. During a total solar eclipse, the innermost parts of the corona are visible to the unaided eye. So something interesting. So far when we do experiments on the sun and observe the sun, the corona is much hotter than the sun itself. So there is a few theories. So one of the theories is for the filaments that causes it to be hotter, but we're going to discuss that in depth later. But so far there's a few working theories on why the corona is hotter, but we can't precisely say why the corona is the hottest part. The observations made with specialized telescopes are called coronagraphs, can block the light of the photosphere and record a corona out beyond 20 solar radii, almost 10% of the way to Earth. Such images reveal streamers in a corona that follow magnetic lines of force in the sun's magnetic field. The corona spectrum, like that of the upper chromosphere, includes emission lines of highly ionized gases. In the lower corona, the atoms are not highly ionized and they are at higher altitudes. And this tells you the temperature of the corona raises with altitude. Just above the chromosphere, the temperature is about 500,000 Kelvin. But in the outer corona, the temperature can reach 2 million Kelvin or more. The corona is hot enough to emit X-rays, but a coronal gas is not very luminous because of its low density. So here in image A and B, nearly two simultaneous images show spun sunspots in the photosphere and excited regions in the chromosphere above those sunspots. So why does the temperature rise as the gas gets further from the core? So that is something interesting we are going to discuss. So last night we had a quick discussion about it. What we know where sunspots are, that is actually magnetic field lines that exits the photosphere of the sun, so the surface of the sun. But when these magnetic field lines get tangled and they break and can't go below the surface of the sun again, I mean, that releases a lot of energy, and we suspect that is why the corona is hotter than the sun itself, because all that energy is now released in the corona, and the corona captures it, and that's why it can emit X-rays and is so extreme. So here we can see here is sunspots. So here in the same image, we can see the sun is more active. Here's two sunspots. So here the sun is more active. Then here we can see the corona extends far from the disk. So here we can see background scars, and here we can see the corona, and the sun hidden behind this mask shows us more of the corona extension. And then here we can see twisted streamers in the corona suggest magnetic field lines that reach us up in the corona. So astronomers have wondered for years how the corona and the chromosphere can be so hot. Heat flows from hot regions to cool regions, but never from cool to hot. So how can the heat from the photosphere, with a temperature of only 5,800 Kelvin, flow out into the hotter chromosphere and corona? Observations made by the SOHO, the Solar and Heliocentric Observatory satellite, have mapped a magnetic carpet of looped magnetic fields extending up through the photosphere. Because the gas in the chromosphere and the corona has very low densities, it can't resist movements of magnetic fields. Turbulence below this photosphere seems to flick the magnetic loops back and forth and whip the gas about, heating the gas. Furthermore, observations with the HINOTE, so Hinode, spacecraft have revealed magnetic wave generated by turbulence below the photosphere traveling up into the chromosphere and corona and heating the gas. In both cases, energy appears to flow out from the interior of the sun to the chromosphere and corona, not by radiation, but by agitation of the magnetic fields. So question, why did I place the sun behind the mask? It is merely to see the corona better. Yes, so we don't want to see the photosphere. We want to see the corona better. So we place a mask in front of the sun, and then the only thing that is visible is the corona. So ionized low-density gas cannot cross magnetic fields. So where the sun's field moves back to the surface, the gas is trapped. However, some of the magnetic fields lead outward into space. And there the gas flows away from the sun in the solar wind that can be considered an extension of the corona. So another hint for tests and exams. I can ask you what is a solar wind, and then you can say it's an extension of the corona. So here we can see, because of the solar wind, the sun is slowly losing mass. But this is a minor loss for an object as massive as the Sun. So the Sun loses about 1 million tons per second of material, or rather matter. So think about 1 million tons of matter per second is what the Sun loses. And can one of you explain to me what's happening here? Yes, it is the magnetic field of Earth protecting us. So remember, we have our solar winds, that is an extension of the corona. Here's the Sun with our magnetic fields. And a magnetic field protects us from the solar wind and other harmful radiation from the Sun, such as X-rays. And you probably have all heard about the northern lights and the auroras. So yes, that is when these high energy particles can enter the Earth's atmosphere through the North Pole or South Pole, where our magnetic field is the weakest, and then it interacts with the atmospheres and it causes the pretty auroras. So let's now look at the composition of the Sun. It seems as though it should be easy to learn the composition of the Sun just by studying its spectrum. But this is actually a difficult problem that wasn't well understood until the 1920s. The solutions of that problem is the story of an important American astronomer who waited decades to get a proper credit for her work. In a 1925 PhD thesis work, Cecilia Payne invented modern methods of interpreting spectra of the Sun and stars. For example, sodium lines are observed in the Sun's spectrum, so you can be sure that the Sun's atmosphere contains some sodium atoms. Payne came up with a mathematical procedure to determine just how many sodium atoms are there. She also proved that if spectral lines of a certain element are not detected in the Sun's spectrum, that the element might still be present, but the gas is too hot or too cool, or the wrong density for that type of atom to have electrons in the right energy levels to produce visible lines. Payne's first calculation showed that over 90% of the atoms in the Sun must be hydrogen, and most of the rest are helium in contrast. Atoms like calcium, sodium, and iron that have strong lines in the Sun's spectrum are actually not very abundant. So here we can see the element, the atomic number, fraction of atoms, and fraction of their mass, all present in the Sun's atmosphere. So almost no light emerges from below the photosphere. So you can see into the solar interior. However, solar astronomers, using a technique called helioseismology, can analyze naturally occurring vibrations in the Sun to explore its depths. Convective movements of gas in the Sun constantly produce vibrations, rumbles, that would be much too low to hear with human ears, even if your ears could survive a visit to the Sun's atmosphere. Some of these vibrations resonate in the Sun like sound waves in organ pipes. A vibration with a period of 5 minutes is strongest, but the periods range from 3 to 20 minutes. So a question, did that table look very weird to anyone else? Yes, that table looks weird. So I got that from the textbook, but it looks weird in the textbook as well, but it looks better in the textbook. Astronomers can detect these vibrations by observing Doppler shifts in a solar surface. Helioseismology requires a huge amount of data. So astronomers have used a network of telescopes around the world, operated by the Global Oscillation Network Group. The network can observe the Sun continuously for weeks at a time as Earths rotate. In other words, the Sun never sets on gong. Helioseismology has allowed astronomers to map the temperature, density, and rate of rotation in the interior of the Sun, as well as to find the positions and speeds of the great currents of gas flowing below the photosphere. That information confirms a model developed to understand the cycle of sunspots and solar activity. So here we can see helioseismology. The sun can vibrate in millions of different patterns or modes. Each mode corresponds to a different wavelength vibration, penetrating to a different level. By measuring Doppler shifts, as the surface moves gently up and down, astronomers can map the inside of the sun. So here we can see the sun's interior, here we can see the surface. And then from here we can see long wavelengths move deeper into the sun. So, can you guys guess what this is? You are partially correct. So yes, this is a form of a solar telescope. But what we are actually doing here is, this is just a normal telescope. And this is just a fancy bracket that goes onto the eyepiece and a piece of paper. So the sun is actually shining through the telescope, and we can see it, we can call it basically a reflection on the piece of paper. And through this we can observe the sun. And if there's sunspots, we can actually see these sunspots. And you guys guess what this is? Yes, Mr. Melville, you are correct. This is a solar filter for a telescope. So this is a specialized filter, a very expensive filter, and you can put it on your telescope, and then you can look through your telescope and actually observe the sun through the eyepiece. So just a reminder, never look to the sun with your naked eyes. But from these observations we can make of these gadgets, we can see the sun is not quiet. It has slowly changing storms larger than Earth that we see as sunspots and unimaginably vast eruptions. In the early 17th century, Galileo observed the sun with a thick dark filter over his telescope and saw spots on its surface. Day by day he saw the spots moving across the sun's disk and rightly concluded the sun is a rotating sphere. If you repeat Galileo's observations, you will probably also detect sunspots. So here we can see in 2002 a few spots, 2003, 2004 is less spots, but here we can see sunspots. And if you look at ultraviolet light, we can see the sun is more violent during those times. So we can see 2005, 2006, 2007, 2008, there's no sunspot, so the sun is actually quiet. 2009 it's quiet, and 2010 it's quiet. So this is actually also something interesting to observe. The dark sunspots that you see at visible wavelengths only hint at complex processes that go on the sun's atmosphere. To explore these processes, you need to analyze images and spectra at a wide range of wavelengths. So 1. Sunspots are cool spots on the sun's photosphere, usually appearing in groups that form and disappear over time scales of weeks and months. So when is the sun going to be active again, or is it already active? So the sun is active again. There's actually currently a few sunspots we can see on the sun. So, but that usually changes within a few weeks or a few months. So sunspot numbers follow a 11-year cycle, becoming more numerous, reaching a maximum, and then becoming much less numerous. The Maunder butterfly diagram shows how the location of the sunspots also changes during a cycle. Then thirdly, the Zeeman effect gives astronomers a way to measure the strength of magnetic fields on the sun and provide evidence that sunspots contain and are caused by locally strong magnetic fields. When the magnetic properties of the Sun are considered, the 11-year cycle is found to be really a 22-year cycle. Then 4. The intensity of the sunspot cycle can vary from cycle to cycle and appears to have almost faded away during the Maunder minimum in the late 17th century. Some scientists hypothesize that this solar activity minimum was somehow connected with a significant cooling of Earth's climate that lasted for several centuries. The evidence is clear that sunspots are part of active regions dominated by magnetic fields that involve all layers of the Sun's atmosphere. So this is how you can also observe the Sun if you have a telescope at home. So you can point it to the Sun and you can have a cardboard box or a piece of paper. And on that piece of paper, cardboard box, you can actually see the sunspots, which is actually very cool to do. So let's talk a little bit more about the Sun's magnetic cycle. So the Sun's magnetic field is powered by the energy flowing outward through the moving currents of gas. The gas is highly ionized, so it is a very good conductor of electricity. When that electrically conducting gas rotates and is stirred by convection, some of the energy of rotation and also energy flowing outward by convection can be converted into magnetic field. This process is called the dynamo effect, and I'm sure you've all discussed the dynamo effect in high school. And it is understood also to operate in Earth's core and produce Earth's magnetic field. Helioseismologists have found evidence that a dynamo effect generates the Sun's magnetic field at the bottom of the convection currents deep under the photosphere. The Sun's magnetic field cannot be as stable as Earth's. The Sun does not rotate as a rigid body. It is a gas from its outermost layers down to its center. So some parts of the Sun can rotate faster than other parts. The equatorial region of the photosphere rotates faster than do the regions at higher latitudes. At the equator, the photosphere rotates once for every 24.5 days. But at latitude 45 degrees, one rotation takes 27.8 days. This phenomenon is called differential rotation. Helioseismology maps the rotation of the Sun's interior, reveal that a gas at different levels also rotate with different periods. Another type of differential rotation. Both types of differential rotation seem to be involved in the Sun's magnetic cycle. So here we can actually see it. So here we can actually see in general, the equator rotates faster than at the North Pole and South Pole. Then here we can see an image B. Detailed analysis of the Sun's rotation from helioseismology reveals region of slow rotation in blue and rapid rotation in red. Such studies show that the interior of the Sun rotates differentially and that currents similar to the trade winds in Earth's atmosphere flow through the Sun. So with the magnetic cycle from the Sun, we can see here the solar magnetic cycle. So for simplicity, a single line of the solar magnetic field is shown. So here we can see a single line. So as the equator rotates faster, that causes differential rotation, and that drags the equatorial part of the magnetic field ahead. Then as the Sun rotates, the magnetic field is eventually dragged all the way around. So at the equator part starts overlapping the northern and southern parts of the Sun. So this differential rotation wraps the Sun in many turns of the magnetic field. So where loops of tangled magnetic fields rises through the surface, sunspots occur. Is everybody still following? Awesome. So although the magnetic cycle is not fully understood, the Babcock model explains the magnetic cycle as repeated tangling and untangling of the solar magnetic field. Yes, we will do a short break. We have one more slide and we can do a break. So sunspots do tend to occur in groups or pairs, and the magnetic field around the pair resembles that around a bar magnet, with one end being magnetic north and the other magnetic south. That is just what you would expect if a magnetic tube emerged from the sun's surface through one sunspot in a pair and re-entered through the other. At any one time, sunspot pairs south of the sun's equator have reverse polarity, meaning orientation of the magnetic field poles, compared with those on the north of the sun's equator. So that's actually quite interesting. So what that means is, if we have a sunspot that has, if you think about a magnet, you have your north and south pole on a magnet. It's the same principle with a sunspot. So if we have one that is a north pole on the northern hemisphere, we will have its buddy on the southern hemisphere that is the south pole. But again, if we have a northern pole on the southern hemisphere, we will have a southern pole on the northern hemisphere. And that is interesting. So these two will actually come in pairs. So this is where the magnetic field lines exit and enters again. So let's take a quick break. So we will restart this lecture at 6:45. So you have about 5 minutes break, 6 minutes break. So, sir, does the sun rotate perfectly perpendicular to the horizontal? Yes. So the sun isn't canted such as Earth is. So the only time today I was not in my office is when I went to get something to eat for lunch, and I were in the building just sorting out a bit of admin, but I was there, and I will be there the next week Tuesday again. So I'm planning to be on campus every Monday and Tuesday from about 10 in the morning to 3 the afternoon. But I can be on campus any other time. Just email me if you want consultation or something pops up, then we can make an arrangement. At 10:30 I was in a departmental meeting. Yeah, so you're more than welcome to pop in next week. So I'll be there. So Mondays are public holiday, so I won't be there, but I will be there next Tuesday again. So usually on Tuesday mornings at 10:30 we have our departmental meeting. But how are your other modules going? WTW, I assume that is a math module. Calculus, the wonderful calculus. What are you doing in calculus now? So I assume that will probably be limits and differentiation. Oh, fun. Those were the good old days. So I made a mistake in my first year by underestimating limits, and limits can be a pain in the ass. What textbook are you using for calculus? So any tips for calculus is practice, 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 and more practice. So we had, in my first year, we had a nice textbook for calculus. And at the end of each chapter, there is usually a bunch of questions you can do. So I would usually try and practice as much as those questions as possible. So what I did is there's a few places where if you know where to look on the net, you can find the solutions manual of these textbooks. So I got my hands on a solution manual and I just worked through all of the problems at the end of the chapters for practice. So single variable calculus, early transcendentals. Yes, that is exactly the textbook I used in my first year as well. So Stewart Early Transcendentals, yes, that's the book. In some way in your second year, you're going to do multivariable calculus as well. That is more fun. But calculus in the first semester is usually the more difficult calculus. And one other thing with calculus, if you are struggling with a concept or don't understand anything, don't wait until the test or exams or anything. Just go for consultation sessions with your lecturer as soon as possible so you don't get a backlog of work you don't understand. Yeah, I understand that. So when you think you're doing it right, and then look at the answers, but you'll get a hang of it. This calculus in first semester is, I know it's horrible, but as soon as you get a hang of it, then everything will be much easier. So let's continue. So now we are looking at the chromospheric and coronal activity of the sun. So the solar magnetic fields extend high into the chromosphere and corona, where they produce beautiful and powerful phenomena. So one, all solar activity is magnetic. The odd shapes of prominences are produced by magnetic fields, and filaments are prominences seen from above. Then secondly, tremendous energy can be stored in arches of magnetic fields. And when two arches encounter each other, a reconnection event can release powerful eruptions called flares. Although these eruptions occur far from Earth, they can affect us in dramatic ways, and coronal mass ejections, so CMEs, can trigger communication blackouts and aurora. And this brings me to an interesting side note. You guys wonder why we don't get any blackouts anymore due to CMEs, so coronal mass ejections or solar flares. Power plants are good at seeing when they are coming so they can prepare for it. Yes, that's one reason. A strengthened magnetic field, not really because of protection. So yes, it's because of protection. The baddest solar blackout was, if I'm not mistaken, in the 1970s. Then almost the entire west coast of the US had no power and no communications. But now we understand how electromagnetism works. We know how electric fields work. We understand how magnetic fields work. So when we design equipment, we know how to properly shield them from the solar flares. So back in the day when there's usually a solar flare, you know you're going to have a couple of days with bad communication, perhaps unstable electricity supplies. But now everything is isolated. So if you look at our power lines are much more isolated. If we look at our communication systems, they are much more isolated. Copper cables are now twisted pairs with layers of isolation. Even our circuit boards that we have inside our devices are now properly isolated with enclosures so we don't have these huge effects from solar flares. So, but I see there are new major solar storms these days, and GPS systems are going haywire. Yes, so our GPS satellites are in geocentric orbit around Earth. So that is some of the satellites that's the highest up in orbit. So those satellites needs to be protected from these solar flares as well. So yes, technology has improved, that we can protect our satellites, but when a solar flare is heading towards Earth, the satellites are going to take the full bulk of the solar flare. So that's why they have solar heat shields and solar flare shields and electromagnetic shields. So usually what they do is when there's a big solar storm, to protect those satellites, they just turn them off momentarily until the storm has passed, and they are turned on again to make sure everything is protected. And that's usually when there's a big solar storm. For the GPS network is done a little bit unstable, but that is due to us protecting the GPS network. In some regions of the solar surface, the magnetic field does not loop back. High energy gas from these coronal holes flows outward and produces much of the solar wind. So here in these images, we can actually see what is going on. So here we can see these magnetic field loops that circles back. And we can actually see these. So here we can see the size of Earth with one of these CMEs. What black auroras are. So I haven't come across the term black aurora yet. So I will read up about it and give feedback in the next lecture. But here in this image, we can see our auroras. So this is in the North Pole. So this is where the magnetic field is emanating. Then it goes around and back to the South Pole. So here is where these high charged particles can enter the atmosphere. And that causes this nice glowing light. So that is actually ionized particles in the atmosphere. And that is what's causing these aurora lights. So now we're going to talk about the solar constant. So even a small change in the sun's energy output could produce dramatic changes in Earth's climate, but humanity knows very little about the variation of the sun's energy output. The energy production of the sun can be monitored by adding up all of the energy falling on 1 square meter of Earth's surface during 1 second. The result, which is called the solar constant, amounts to about 1,370 joules per square meter per second. So if we convert that into watts, then that is about 1,397 watts per square meter. So that is why solar energy can be sufficient. But you guys guess what is the only drawback why our solar energy is not as efficient yet? Not whether, that is literally due to the effectiveness of our solar panels. So the best solar panels or photovoltaic cells we have is currently at, I'm rounding up to more or less 40% efficient. So from that odd 1,300 watts per square meter we are getting, with these solar cells we have currently, we are only getting about 40% of that power. So 40%, so we are roughly, what, 40%? Getting between 300 to 400 watts per square meter. So that is why there's a lot of development going into solar energy. So we want to get photovoltaic cells and solar panels that are a lot more efficient. So back when solar panels came out, they were about 6% efficient, 12% efficient. So now we are about at 40% efficient. But it would be great if we can get that number as close to 100% as possible, because then we will have more power than we can tend to use. Isn't the sun's diameter changing? Well, very slowly, and thus the solar constant won't necessarily stay the exact same. Yes, that is true. And that is where everything leads up now, what we're going to talk about now. Then we need biological mimicry of photosynthesis plants. That is actually a very interesting idea. So let's go back to the slide and let's have a little bit of a discussion first. So what can you guys tell me about nuclear fusion? Yes, it is very difficult to replicate. You are correct. Dangerous, fussing atom, fusion atoms, little waste. The reaction is based off mass. Center of the sun is so dense, atoms fuse, squishing atoms together, need a lot of energy, high energy production. So yes, so the sun creates energy in the forms of fusion. So let's discuss fusion a little bit. So the sun is a ball of hot gas held together by its own gravity. If it were not for the sun's gravity, the hot, high-pressure gas in the sun's interior would explode outwards. Likewise, if the sun were not so hot, its gravity would compress it into a small, dense body. So remember, for nuclear fusion, there are two things that is very, very, very important to keep the reaction alive. So the one is the sun's gravity, and the other one is the sun's heat or temperature. So the sun generates energy by breaking and reconnecting the bonds between the particles inside atomic nuclei. There are only 4 different ways in which matter affects other matter. The 4 forces of nature, so gravity, the electromagnetic force, the weak force, and the strong force. So there are 2 ways to generate energy from the atomic nuclei. Nuclear power plants on Earth use nuclear fission reactions that split uranium nuclei into less massive fragments. A uranium nucleus contains a total of 335 protons and neutrons, and when it decays, it splits into a range of possible fragments, each containing roughly half as many particles. Because the fragments that are produced are more tightly bound than the uranium nuclei, binding energy is released during uranium fission. And I know I've said this in a previous lecture, but for the sustainability of humankind, it is very, very, very important that we switch over to nuclear fission or nuclear power. So when you look at this normal power plant, would you say this is pollution? No, you guys are incorrect. This is not pollution. This is steam. So here on the left, we can see the nuclear power plants. So they use the nuclear power to heat up water. The steam spins turbines, and that creates energy. But that hot water needs to be cooled down, and that is pumped into these cooling towers. So this we see on the top is steam and not pollution. So from a nuclear reactor, we are not getting any pollution. And as I said before, and that irritates me about how naive people can be, nuclear power is one of the cleanest forms of energy. So everything comes down to the conservation of matter. So conservation of matter is the same as the conservation of energy. So matter cannot be created nor destroyed. They can only be transformed from one form into another. So in a nuclear power plant, if you use 2 kilograms of uranium-235 as fuel, you're going to get 2 kilograms of uranium waste out the other side. And people think these fuels are barrels and barrels and barrels and barrels of the stuff. But in essence, a typical nuclear power station only uses about 2 to 3 kilograms of uranium in a year. So that is not much waste whatsoever. And then people say, oh yes, but where do you keep the waste? What do you do with the waste? But what people don't realize is, if you dig deep in the Earth's mantle, the mantle actually becomes radioactive. So right here in Gauteng, more precisely on the west rand of Johannesburg, is the deepest mines in the world. I'm not sure about the correct numbers, but the last time I checked, I think Crown Mines had a deepest mine on the West Rand, and the deepest mine in the world. I think it's roughly 3.4 kilometers deep. They are planning on expanding it to about 4 kilometers. I'm not sure if they reached the 4 kilometer mark already, But if you dig that deep, round about 3 kilometers deep in the ground, the mantle becomes radioactive. So what do you do with nuclear waste? You dig a big hole, such as the mine, 3 kilometers deep as possible, and you store all your nuclear waste there. So now you have already a radioactive environment that is naturally radioactive, and you just keep your other radioactive material with it. So no problem whatsoever. But people have a complete misunderstanding of nuclear energy. And I wish people would realize this. So this is actually very interesting. So let's see, Mr. Watson. So with a complete combustion or fusion, approximately 8 kilowatt hours of heat can be generated from 1 kilogram of coal, approximately 12 kilowatt hours from 1 kilogram of mineral oil, and about 24 million kilowatt hours from 1 kilogram of uranium-235. So yes, you get a lot of energy. So that is why there's a common misconception, especially in South Africa. There is people are afraid of nuclear power, and that shouldn't be the case. We should be embracing nuclear power. For example, if you take a US aircraft carrier, it has a nuclear reactor on board the size of a normal wheelie dustbin that you have at your houses. They use about 20 kilograms or 22 kilograms of uranium in 20 years for fuel on an aircraft carrier. And can you guys guess what this is? So yes, you are correct, because of Fukushima and Chernobyl and what's it, the Malong Island, people are afraid, but those are minor setbacks. So this image right here is a nuclear reactor. Do you guys know how this reactor works, or what is the basic principle of this reactor? So what happens is, so here in the middle, you will see is this box, and it looks like these round metal shafts. So what's happening with these metal shafts is we have two types of shafts. So usually there will be one that's uranium shaft, and the other one is empty hole. Then there's another uranium shaft and another empty hole. Then what is happening in these empty holes? You have lead staves, lead or sometimes graphite, but right now in modern reactors, it is lead that slips into these holes. So if you think about, what's a good way to explain this? So let me get the whiteboard out. It will be the easiest to explain it this way. So we will have our uranium staves fixed in the reactor. And then we will have from the opposite side our lead staves. So that will be fixed into a mechanism that holds them. And there will be staves being pushed down into those holes called lead. So what's happening is, if you want the nuclear reactor or the reaction to happen faster, you actually lift out these lead control staves or control rods. You're correct, Mr. Henning. We lift them out of the reactor, and then the reactor, the reaction is speeding up and we get more energy. And if we want the reaction to be smaller or the reaction to die down, then we push down these control rods or these lead rods into the reactor. And these rods are the fuel we are using. So those rods get replaced, but that is the essence of a reactor. So what's happening is, what it is, we call them control rods, those lead rods, is when we remove the rods, the uranium gets split into two, and that atoms get split faster, and that's basically a runaway effect. But if we push down the lead staffs into the reactor, that actually absorbs the particles and the electrons that's being split, and that breaks the reactor and can even cause it to stop. And then the water where this is in, we call this cold water, or there's another term, I can't remember the exact word for it now, but basically in essence is this, the water has no minerals in heavy water. Yes, that's right, Mrs. Swanepoel, thank you. So it's called heavy water, but it has no minerals in, no impurities in, and that is to make sure that some of the reactions are also absorbed by the water itself. Something interesting, Palindaba, that's in Hartbeespoort Dam, its new name now, it's Nexa. That is where that was a nuclear reactor. There is still a nuclear reactor. Originally, it was used to develop South Africa's nuclear weapons program, but since the 1994 elections, South Africa has dismantled their nuclear weapons. So we have no nuclear weapons anymore, but we did have nuclear weapons. We had actually 6 nuclear warheads that was developed by the old Palindaba. But reactor now at Palindaba, or now called Nexa, is used for nuclear research and nuclear medical research. So you can go to visits at Nexa, but something interesting is a couple of years ago, 2 students committed suicide by actually jumping into the heavy water next to the reactor. So now they are actually quite strict. So if you are studying and need to do work on the reactor, then you need to do a psychological test beforehand to make sure that you are stable enough and do not try to commit suicide inside the reactor. So, stars don't use nuclear fission. They make energy in nuclear fusion. So did I contaminate the reactor? No, luckily they did not contaminate the reactor, but I had to shut down the reactor, they had to remove the bodies. Now the bodies are radioactive, so it was a big mess. So that's why, and they were postgraduate students, I think working on PhDs. So now to get access to the reactor, you need to go through a psychological test as well. So they make energy in nuclear fission reactions that combine light nuclei into heavier nuclei. The most common reaction inside stars, that one that occurs in the sun, fuses hydrogen nuclei, so single protons, into helium nuclei, which contain 2 protons and 2 neutrons. Because the nuclei produced are more tightly bound than the original nuclei, net energy is generated. So how did I dispose of the bodies? I actually have no idea. Sir, do you support nuclear war? So I do not support nuclear war, but on my scientific site says it's amazing technology, but no, we cannot afford a nuclear war. So the biggest nuclear war, nuclear weapon currently Russia has one. It's called the Tsar bomb. And the Tsar bomb has the power, if it's dropped somewhere, it will level an area the size of Texas. So that's why it's amazing technology, but we cannot afford a nuclear war. So I think it was in last night's lecture when someone mentioned the artificial sun that China is working on. So it's not actually an artificial sun, but it's actually a nuclear fission reactor where we will fuse 2 atoms together. And this is inside how one of these reactors will look like. So the Chinese, there's actually a few research groups around the world working on it. So the Chinese call it a tokamak reactor, well, the design, and you need immense magnetic fields to keep the reaction stable. So inside the reactor, it will actually cause a plasma that we can see with the fusing process. but it is very unstable, but that is basically how the sun works. So, sir, do nukes stop wars from starting? I have no idea. The only place in history where a nuclear weapon was used in a war was in World War II on Hiroshima and Nagasaki, and that stopped the Japanese from, well, they surrendered after that. So the question rather is, does the means justify the ends? So as you stop to nuclear reaction, is there a way to reverse a reaction with lead in somehow? Since lead is used to stop a nuclear reaction, so if you want to restart the reaction with lead, we just remove the lead control rod, so move them out of the reactor again, and then the process is starting up again. So here we can see the orange curve in this graph shows the binding energy per particle, the energy that holds particles inside an atomic nucleus. The horizontal axis shows the atomic mass number of each element, the number of protons and neutrons in the nucleus. Both fission and fusion reaction reactors move downward in diagram arrows, meaning the nucleus produced by a reaction is more tightly bound than a nucleus that went into the reaction. Iron has the most tightly bound nucleus, so no nuclear reactions can begin with iron and release energy. So here we have reasoning with numbers, hydrogen fusing. So when 4 hydrogen nuclei fuse to make one helium nucleus, a small amount of matter seems to disappear. To see this, subtract the mass of helium nucleus from the mass of 4 hydrogen nuclei. Then we can see the difference. So the mass difference of 0.044 times 10 to the power minus 27 kilogram does not actually disappear, but is converted into energy according to Einstein's famous equation, E equals mc squared. So here we can see it's 4 times 10 to the power minus 12 joules. But recall that 1 joule is approximately equal to the energy of motion of an apple falling from the table to the floor. So in this image, we can see the proton-proton chain combines 4 protons to produce 1 helium nucleus. So energy is produced mostly as gamma rays and as positrons, which combine with electrons and convert their mass into more gamma rays. And then neutrinos escape without heating the gas. So here we can see our hydrogen forms a helium. And so the process continues. So how does energy transport in the sun occur? So you will learn in a later chapter that astronomers have computed models indicating that the temperature of the center of the sun must be about 16 million Kelvin for the sun to be stable. Compared with that, the sun's surface is very cool, only about 5,800 Kelvin. Heat always moves from hot regions to cool regions. So energy must flow from the sun's high temperature core outward to the cooler surface where it is radiated into space. Because the core is so hot, the photons there are gamma rays. Each time a gamma ray encounters one of the matter particles, electrons or nuclei, it's deflected or scattered in a random direction. And as it bounces around, it slowly drifts outward toward the surface, while being converted into several photons of lower energy. The net outward motion of energy is in the form of radiation. So astronomers refer to the inner parts of the sun as the radioactive zone. Energy, originally produced in the core of the sun and traveling outward as radiation, eventually reaches the outer layers of the sun, where the gas is cool enough that it is not completely ionized. Such material is not very transparent to radiation. So at that point, the energy backs up like water behind a dam, and the gas begins to churn in convection. So hot blobs of gas rise and cool blobs sink. In this region known as the convection zone, the energy is carried outward not as photons, but as circulating gas. So if we visualize this, here we can see our photons are bounced bound, scattered around, and that is our gamma rays. Then we have our energy reaching upwards. So we can see a cross-section of the sun. Near the center, nuclear fusion reactions sustain high temperatures. Energy flows outward through the radioactive zone as photons or randomly deflected over and over by electrons. In the cooler, more opaque outer layers, the energy is carried by rising convection currents of hot gas, so the red arrows, and sinking currents of cooler gas. So when the energy starts rising here, we can see a hot gas going up, cooler gas sinking back down. So nuclear reactions in the sun's core produce floods of neutrinos that rush out of the sun and off into space. 100 trillion solar neutrinos flow through your body every second, but you never feel them because you're almost perfectly transparent to neutrinos. If you could detect these neutrinos, you could probe the sun's interior. You can't focus neutrinos with a lens or a mirror, and they zip right through detectors used to count other atomic particles. But neutrinos of certain energies can trigger the radioactive decay of certain atoms. That gives astronomers a way to detect neutrinos. In the 1960s, chemist Raymond Davis Jr. devised a way to count neutrinos produced by hydrogen fusion in the sun. He buried a 100,000-gallon tank of cleaning fluid in the bottom of a South Dakota gold mine, where other types of cosmic rays could not reach it, and devised a way to count individual argon atoms that were produced by neutrinos colliding with chlorine atoms in the tank. The Davis neutrino experiment created a huge controversy. It was expected to detect one neutrino a day, but actually counted 1/3 as many. Only one neutrino was captured by that 100,000-gallon tank over 3 days. Were scientists wrong about nuclear fusion in the sun? Did they misunderstand how neutrinos behave? Was the detector not working properly? Because astronomers had reason for confidence in understanding of the solar interior. They didn't abandon those hypotheses immediately. It took over 30 years, but eventually, physicists were able to build better and different detectors. So this right here, image on the left, is the Davis solar neutrino experiment. Used cleaning fluid and could detect only one of the 3 flavors of neutrinos. Then in image B, the Sudbury Neutrino Observatory is a 12-meter diameter globe containing water-rich deuterium. So that is heavy hydrogen. So it's an isotope of hydrogen in place of ordinary hydrogen, buried 2,100 meters down in an Ontario mine. It can detect all 3 flavors of neutrinos and confirms that neutrinos oscillate. How fast are neutrinos? I'm not actually sure. I'll check that for you. I may be mistaken, but they should almost be traveling at the same speed as electromagnetic waves, but I may be wrong. So that, ladies and gentlemen, is tonight's lecture. So I hope you enjoyed the lecture. For those of you writing semester tests this week, good luck with your tests. Remember, next week, Monday, is a public holiday. And then I will see you all in next week, Tuesday's class. Okay, so a few questions. I'm seeing like gravitation answers here. I'm seeing almost the speed of light and faster than the speed of light. I will actually check where this is scratched. So where are neutrinos located in the atom? So neutrinos are some of the, say, the neutron of the atom, if I'm not mistaken. So I just want to make sure which textbook we need to buy. The study guide prescribes Horizons Exploring the Universe, but you suggested, so you will see there's prescribed textbook and additional reading textbook. So the prescribed textbook is Horizons Exploring the Universe, the 14th editions. The others are just additional textbook that you can look through at your own time if you want to do a few e-reads, but we are using the Horizons textbook. Then, sir, why do these convections form in the sun? Why does everything not try to get as close as possible to the center of the sun? So that is due to, that will be discussed in the next chapter, but that is due to the gravitation of our own sun, and also on the temperature. So we will soon learn the sun has a gravity temperature thermostat sort of that controls the rate at which the reactions occur, but also controls everything. So we will learn how these two are used to get everything as where they are. So how fast can the hydrogen collider split atoms? So I'm not actually sure, but I think that is something like 0.8 or 0.9 the speed of light. So which tract of textbook was this lecture from? So this was from lecture, so chapter, I think 7. Pleasure, guys. So if there's no further questions, then I will see you all next week. So, sir, we have no class on Monday, and is the test due next week, Friday? So, yes, you have no class on Monday. And then the quiz you have will open up on Monday and close on Friday. So you will be able to do it anytime you wish next week. So question, how do neutrinos even travel that fast? Because they are the same particle as matter, so they would have such high mass traveling that speed. I'm actually not sure, so my forte is not particle physics, but I will find out for you. Also made a pretty cool graph if you want to see. Yes, you can share me a pretty cool graph. I don't know if you'll be able to share it now. Let's see what I can do. Okay, cool. Let me open up your link. That is pretty cool. So if there's no more question, you guys, then I'm also going to log off. So have a great week. Good luck with tests and assignments, and I will see you all next week. Good night, everyone.